So this is the third class of Fourier series, and in this class just I am going to discuss about the recapitulation of my previous class, that is a periodic function. If this function is well defined and this function is periodic and this function is bounded in a closed interval, then within that interval this function can be represented as sum of this n equal to 1 to infinity an cos nx plus bn sin nx. Right? Now you can put this a0 by 2 term in within this cos function, so you can write a equal to 0 to infinity an cos nx plus bn sin nx. So a periodic function is nothing but a combination of cosine series and of course sine series. Alright, so what does it mean? This n represent, if you say that this n represent some frequencies of some wave whose combination or linear combination gives me this fx function, then what I should say, that a function can be either split into several number of frequency dependent sine and cosine functions, or I can say that if you add some sine and cosine, all types of sine and cosine function having frequency from 0 to infinity, but see here, if n equal to 0, then this term gives me 0, so b0 is 0, so b0 so the contribution of this b0 sin nx will be 0. So n equal to 0 you can combine here, but do not write this n equal to 0. So summation n equal to 0 to infinity bn sin nx is also possible, but n equal to 0 gives me 0. Right? So if you choose all frequencies, all types of frequency, and you add them in a series form, you will get this periodic function ultimately. Okay, so and what is the basis of determination of this coefficient? Because you can determine this coefficient as a matter of fact that it represents the orthogonality condition of cos mx when m not equal to n. Right? So this orthogonality condition ultimately responsible for determination of this an and bn. Okay, so if there is no orthogonality relation between the different coefficients of cosine series or different coefficient or different frequencies of sine series, then you cannot determine this an and bn term. So what does orthogonality means? In case of vector, just remember that orthogonality means two vectors are just perpendicular to each other. Now the dot product, if the dot product between two vectors is 0, a dot b is 0, then you can say that these two vectors are orthogonal to each other. The same thing happens here. So you choose a basis function fx and you are going to expand this function in terms of several sine and cosine series. Now if you choose several frequencies sine and cosine series, if this orthogonality holds good for different coefficient of either cosine series or sine series, not only that, if this relationship hold for cross term either sine and cosine series, then you can say that this function can be determined, right? So within a bound limit minus pi to plus pi, this orthogonality relation holds good. Okay, not within all range of pi, but within minus pi to plus pi, you can say that, definitely say that this cross term have orthogonality relation. So orthogonality relation is the basis of determination of this coefficient of Fourier series. Okay, so what does Fourier series physically means? Physically means that, say for example, you choose I expand all the term of a function fx in Fourier series. What you will get? Sum a0 by 2. This is obviously cosine function with n equal to 0. a1 cos x plus a2 cos 2x plus in this way up to infinity. And in case of sine series, b1 sine x, b2 sine 2x, b3 sine 3x, in this way. So here the frequency is 1, here the frequency is 2, and ultimately in the next term the frequency is 3. In such way, in sine series 1, this is 2, this is 3, and so on. This is also an infinite series. So if you can determine this coefficient a1, a2, which you can definitely determine from the orthogonality condition, and if you can determine this b1, b2, b3, etc., you will definitely get this function. So now what does it mean? A sine x, if you draw a sine x function, just like this. Now if you draw sine 2x, its frequency just double. So for sine 2x, in twice, this is pi by 2, this is pi, this is 3 pi by 2, this is twice pi. Okay, now if you choose, this is sine function, if you choose sine 2x, what does it mean? In pi by 4, the function gives double. Okay, so function is like this. Its frequency just double than that of this. Now if you choose sine 3x, so what does it mean? This is pi by 2. So in pi by 3, the function will gives me maximum value. Okay, and somewhere the function becomes here. Okay, so frequency increase, same thing happened for the cosine series. So if you choose different types of frequency and add them, what you do? You just make some superposition of all types of frequency range and you will get these things. Remember a thing in case of determination of phase velocity and group velocity, you have just done the same thing. You have combined all those frequencies together to get a function, right? So this is the physical significance of Fourier series. Why we are using a Fourier series for determination of a function fx, right? So I think you can understand the physical significance of Fourier series, why it is so important in physics. Now I am going to tell you some different thing, that is, if you can expand a Fourier series in either sine or cosine function, then this function may be even or odd. Okay, now what does it mean if x even or odd? Even function means if you expand this function in minus x direction, so you get fx. This is x equal to 0. Now if you choose this type of function, okay, what is this? This is a cosine function. Now if this function is symmetric with respect to x equal to 0 axis. Okay, so left hand side is just same as right hand side about x equal to 0. So this even function must be symmetric with respect to a definite point that x equal to 0. Okay, now in case of odd function, there is no symmetry minus fx. Okay, it just reverses its direction. So if you choose a sine function, it will gives me just this. Okay, so from minus 5 to plus 5, this is minus 5, this is plus 5. What you will get? You get the just this reverse direction of this wave, but the nature of the wave remains same. Okay, so nature remains same, but just this wave reverses itself. Okay, so that is odd function. So example is sine x. Right? So how could you expand? There is a proposition for Fourier expansion for even function and odd function. So what are the propositions? Now the proposition is for calculation only, because the calculation is as it is complicated. So if you remove any of the term initially, then the determination becomes easier. Okay. So if you expand for an even function, now for even function, if minus x equal to fx, and you want to expand this function in the limit, in the bound region minus pi to plus pi. So from 0 to minus pi and 0 to plus pi, this function remains as it is. It remains as fx. So as it remains as fx, then you can say that integration from minus pi to plus pi fx dx equal to 2 times 0 to pi fx dx. So you can make the whole range to a half range series. So this is the full range series, minus pi to plus pi. And for the even function, you can change it to the half range series by multiplying just a 2 factor because of its symmetry around x equal to 0 point. Right? So the coefficient, Fourier coefficient in case of even function becomes a0, what is that? Integration 1 upon pi, integration minus pi to plus pi fx dx. Now, as it is a symmetric function, you can use the symmetry property of this function. So, a0 becomes 2 divided by pi integration minus pi to plus pi fx dx. Okay. An similarly 1 upon pi integration, this becomes minus pi to plus pi fx dx, fx into cosine mx dx. This is just a dummy index, so you can change it either m or n. Right? So, as this is even function and this mx is also an even function, so you are using a combination of two even functions. So the coefficient an becomes just 2 divided by pi 0 to pi fx cosine mx into dx, where m is integer except 0. Right? So you can get n, and what are the values of this bn? Now bn becomes similarly 1 upon pi minus pi to plus pi fx sine mx dx. Now this function is an even function and this function is an odd function. So you choosing a combination where you are going to multiply an even function and an odd function, and you are going to take the integration of these two functions within a closed boundary range of 0 to twice pi. So within this range, twice pi range, you are going to integrate the combination of this odd and even function. So if you're going to combine this odd and even function within this range, definitely the value of this term will be 0. Okay, so for a even function fx, what you will get if fx is even, then a0 equal to 2 by pi 0 to pi fx dx, an equal to 2 divided by pi 0 to pi fx cosine mx dx, and bn equal to 0. So you have to use this property for calculation of Fourier series in case of an even function. Now what happens if you choose fx as an odd function? So choose fx as an odd function. Now what is the property of this odd function? The property of odd function is that fx equal to minus of fx, f minus x equal to minus of fx. Now if you choose this odd function, then what you will get when you expand this in Fourier series? So for odd function, if you integrate minus pi to, or the range between minus pi to pi, if you integrate from minus pi to plus pi of this fx dx, what you will get? Assume that this is your antisymmetric function or a odd function. Now, what does this fx dx means? This is the area under this curve, right? So this area is just same as this, and you are going to add these two area. Okay, the effect becomes 0 because the direction of this area are different. Okay, so if you choose this integration must gives you the value 0. So as I choose this thing, you can definitely say that the value of a0 is 1 upon pi minus pi to plus pi fx dx. This will give me 0. Definitely. And in the similar proposition, I can write that an equal to 1 upon pi integration minus pi to plus pi, obviously fx cosine mx dx. This fx is an odd function and this cosine mx is an even function, right? So you are going to multiply an even function with the odd function and then you are going to take the integration. What does it mean? You are choosing an even function, symmetric function, and you are going to multiply same thing with an odd function here. Okay, just multiplication. Now what will happen? When you are going to multiply this term with this, it will automatically reverse its direction, right? So same thing happens for this multiplication. So as its area will be reversed when you multiply in case of x in negative x direction, then the integration of this term will give me 0. Okay, so even function, odd function, integration within a closed interval minus pi to plus pi gives me the form 0. Now, what is the value of this bn? This will be 1 by pi minus pi to plus pi fx sine nx dx. Okay, so as fx is an odd function and sine x is an odd function, so when you multiply two odd function, this is an odd function, and again you will multiply the same thing with a different odd function. What will you get? You get an even function. Okay, so the integration between minus pi to plus pi for the multiplication of two odd function gives me an even function. So what is the value of this? So this will be 2 by pi 0 to pi fx sine mx dx. So this will be the value of this integration, right? So this is obviously the form when you use this odd function. Now, as you propose that the odd function, we can write this in terms of a series where we use just not the full range but when you use this full range, you can transform this full range into a half range series. So this is called a half range series, right? So you can transform for either the even function or the odd function in terms of, not in terms of full range series, but you can transform this into the half range series. So this is called the half range series. Now, what is the half range series? Either this is a half range cosine function. So half range cosine function. Now, what is the form of this half range cosine function? The form of this half range cosine functions become fx equal to a0 by 2 plus sum of n equal to 1 to infinity and if you use any interval of range, not only minus pi to plus pi, but you use minus L to plus L, and this range, this cosine function will be an of n pi x divided by L, right? So you will get just the cosine function for cosine series. Now, what is the half range sine series? Now, half range sine series is fx equal to sum of n equal to 1 to infinity. This is bn sine n pi x y. So when you transform this range to pi to plus pi, automatically this becomes pi x and this becomes pi x, right? So this is the complete representation of half range cosine series and half range sine series or any Fourier expansion. Now the another thing remains, that is Parseval's theorem. So what is Percival's theorem? Now Percival's theorem tells me that if you take the average of square of a function in its bound interval range, and the preliminary condition is that this function must be well defined and this function must be periodic, and this function is we can use this function for Fourier expansion. So this is the preliminary condition for this function within the bounded interval. Then the average of the square of this function in the bounded interval is just the sum of its Fourier coefficient. Okay, so you can say that if you can expand a Fourier series, you should not go for just integration of the square to determine this average, but if you add all the Fourier coefficient term, you can get the value of this square of fx. Okay, so I can write here that 1 upon pi, like 1 upon twice pi, because this function is obviously within the range minus pi to plus pi, integration minus pi to plus pi fx square into dx. Okay, now if you choose fx square into dx, this function can have a Fourier expansion. So if you choose this function, so fx equal to a0 by 2 plus sum of n equal to 1 to infinity an cos nx plus bn sin nx. Okay, so a0 by 2 plus an cos nx bn sin nx. Now if you just square this function, so what you will get, fx square, this will be a0 divided by 2 plus sum of n equal to 1 to infinity an cos nx plus bn sin nx square. Right? So what you will get here, you will get a0 by 2 square plus sum of n equal to 1 to infinity an cos nx plus bn sin nx, just square of this, plus a0 into 2 is obviously a0 into sum of n cosine nx plus bn sin nx. Okay. So what you will get this thing. Right? So when you are going to integrate within minus pi to plus pi of this function, you are going to integrate minus pi to plus pi times dx. The same integration comes here, so minus pi to plus pi within third bracket times dx. So what you will get, again you are going to use the orthogonality condition. And you are going to use the integration of a cosine series. It becomes for minus pi to plus pi. So the result will be, obviously if you add all the cosine term for a series, you will get that this cross term integration becomes 0, and definitely the sin x becomes 0. Okay, now if you use here, from here what you will get, you will get either an square cos square nx, bn square sin square nx. So I just remove the next term and I am going to write what you will get. So leave this term here. So for this you will get an square cos square nx, obviously sum remains here, plus 2 an bn cos nx sine nx, but this n and n are different because this two function may be same, may not be same. Okay, and you get bn square sine square nx. Right? The sum runs from n equal to 1 to infinity. But when you get this cross term, you use the condition of orthogonality for different sine and cosine functions. Not only that, when this cosine function, this dummy index become different, you can use the same orthogonality condition for this cross term, cosine mx, cosine nx, where n not equal to n. So those terms you're going to integrate from minus pi to plus pi, and you just integrate this term, the cross term having different cosine indices or different frequency, they gives me 0. And obviously this term, if you are going to integrate, this will gives me even 0. So what you will get when you're going to integrate these things, you have just remain these two terms in your hand. So bn square sine square nx into dx. Right? Now, if these two terms remain in your hand, what you will get, that the value of integration minus pi to plus pi, 1 upon twice pi f x dx, this will be integration minus pi to plus pi a0 square by 4 into dx plus an square, obviously sum remains at n equal to 1 to infinity, minus pi to plus pi cos square nx dx plus sum over n equal to 1 to infinity bn square integration minus pi to plus pi sine square nx times dx. Right? So, sorry, here one term I am missing, that is 1 by twice pi is here. So what you will get, from this term, you will get that this dx, this gives me just pi minus pi, so twice pi. So what you will get from this, that this gives me a0 square by 4 plus this is sum of n square, sum of n square. Okay. So this is just Parseval's theorem. So you did not integrate this because this term gives me what is, this is cos square nx. So the cos square nx means 1 plus cos 2nx, and we are going to integrate minus pi to plus pi times 2x. So this term will be 0, and same thing happens for sine square nx. This is 1 minus cos 2nx. Okay, in the case of sine x. So you will get just this as the Parseval theorem, right? So 1 upon twice pi integration minus pi to pi fx dx. This will be a0 square by 4 plus n square plus p square. So just the sum of this coefficient n equal to 1 to infinity. Oh, sorry, this is fx square. Okay. So average of a function, square of a function within bound interval, this is just the sum of this Fourier coefficients. Okay. So now let us consider a famous function, that is delta function. Now what is a delta function? A delta function gives me 1 at x equal to 0 and 0 otherwise. So if you draw the curve of this delta function, what you will get, in the vicinity of x equal to 0, the function gives a sharp rise, and in both sides this becomes 0. So this is a symmetric function. You can write this as a symmetric function, so even function, right? So as this is an even function, this is an even function, you can expand this delta function in terms of Fourier series. So what you will get? You will get that a0. So if so first let us write this delta function in terms of Fourier series. So this will be a0 by 2 plus sum of n equal to 1 to infinity an cos nx plus bn sin nx. Now you have to calculate this a0, an and bn from the definition of this delta function. So a0 will be 1 upon pi integral minus pi to pi delta x dx, and definitely if you integrate this delta x dx within a closed interval minus pi to plus pi, what will be the area of delta x under the curve? The area always becomes 1. So as the area always becomes 1, so 1 upon pi delta x into dx, this will give me just 1 upon pi into 1. So 1 upon pi. Right? So for any delta function, the area delta x dx, this becomes 1 always, if you integrate it in a closed interval. Now, as this is a symmetric function, so I can easily say that bn becomes 0 for this function. So bn equal to 0. Okay. Now, what will be the value of this an? So an equal to 1 upon pi minus pi to plus pi delta x times cosine nx dx. Right? So if you, this will be 1 upon pi minus pi to plus pi delta x cosine x nx dx. Now what is the value of this an? Because this function is valid in the vicinity of x equal to 0. And in the vicinity of x equal to 0, the cosine nx gives me just 1. So cos 0 equal to 1. So this cosine nx in the vicinity of x equal to 0, this gives me 1. So delta x times cosine nx. So the function, the value of this function is 1 at x equal to 0, and value of this cosine is equal to 1 at x equal to 0. So again, the term will be 1 upon pi. Okay, so for delta function, what I will get, a0 equal to 1 upon pi, an equal to 1 upon pi, and due to symmetric property of this function, bn equals to 0. Now you expand this delta function in terms of this Fourier coefficient. What we will get? We will get that the delta function consists of 1 upon pi plus 1 upon pi sum of n equal to 1 to infinity cosine nx. Okay, so what you will get, 1 upon pi. Similarly here we can get cos 0 as 1. So sum of n equal to 0 to infinity cosine nx. So n runs from 0, 1, 2, 3, 4. So you generate a delta function when you add all types of cosine function with this type of frequencies. So from if you add all the cosine frequencies from 0 to infinity, you will generate ultimately a delta function. So you can expand delta function in terms of Fourier series. In the reverse direction, I can say that if you add all this cosine function, you can generate a function. So Fourier series is nothing but the sum of different periodic function to generate a specific function. So Fourier series can be represented as Fourier sum, right? So I can write here that this delta function is nothing but 1 upon pi cos 0x plus cos 1x plus cos 2x plus cos 3x. Okay, so definitely if you use the form of this cosine 1x, what we will get? We will get this within plus pi to minus pi. So minus pi, this becomes 1 and plus minus 1. Okay. Now you are going to add cos 1x. Okay, so this is cos 1x. And cos 0x, this gives me 1 always. So this becomes 1. Cos 2x, the frequency becomes double. So this is pi by minus pi by 2. This is pi by 2. So what you will get at pi by 2, as this is twice x, so this function remains as this. Okay, now you add cos 3x. So this is pi by 3. So you are going to add this function. 5 pi by 3, 4 pi by 3, you are going to add this function. So you are adding all this function to generate a delta function. Right? So this is the significance or the beauty of a Fourier series. Right? You can generate a function by doing sum of all types of frequency. So this Fourier series is so important in case of either quantum mechanics, mathematical physics, even in case of sound, even in case of communication system, where there are numerous number of frequency waves coming and they are going to superpose to generate a definite types of frequency. So this is the end of this Fourier series third class, and thank you.